We are now going to discuss the third method to add the vectors. This is called the analytical method by using vector components. So, if we have two vectors, a1 and a2, you have learned that we can add these vectors by using parallelogram method or polygon. So here I'll show you again. We add these vectors by using parallelogram method. You have to have parallel line like this, and the diagonal of this parallelogram is the resultant of vector a1 and a2. In other words, we can say that vector a can be created by using vector a1 and a2, or also we can say that vector a1 and a2 are the components of vector a. But there are also some special components of vector. In the case here, we have vector ax and ay, and they are perpendicular each other. So ax is parallel to the horizontal axis, and then ay is parallel to the vertical axis. And if we add ax and ay here, we will also get vector a. So again, the vector ax and ay here are the components of vector a. Now, our goal is to find the relation between vector a and ax, or vector a and ay. Before we do that, let me remind you again about the right angle triangle. Now we have a right angle triangle like this. So this has opposite side y, adjacent side x to the angle theta here, and then the hypotenuse z. Now from the trigonometry you have learned that sine theta is equal to the opposite side y divided by z. So from this relation we can also write that the opposite side y here is z times sine theta. Now the second side is x. We can also write that cosine theta here is equal to x divided by z. So x here is equal to z times cosine theta. Therefore, we can always use this relation to find the value of y or the value of x by using z and sine or cosine theta. Now we have this situation where we have vector a and its components ax and ay, and there's an angle here theta. So if we redraw this vector, this is ax, ay, a and theta. Now you know that sine theta is ay divided by a. So this is the opposite side of theta. Therefore, AY here is A times sine theta. And now we can find AX, since cosine theta is equal to AX divided by A. Therefore, the magnitude of AX is equal to A times cosine theta. You should not memorize this relation because that depends on the position of the angle here, theta. If you have different position, for example, if theta is here, then this will not apply anymore, and then you will need to think about it again. Now we will have some practice to find this value of AX and AY. Suppose this is AY, AX, and then the angle here is 30 degrees, and the magnitude of vector A is 10 centimeter. So now, as you learned from previous slide, the AY is equal to A here 10 times sine 30, and the value of sine 30 is 1/2, so you get 5 centimeter. And the AX here is 10 times cosine 30, and cosine 30 is square root 3 divided by 2, so you get 5 times square root of 3 centimeter, or this is around 8.66 centimeter. Now we have the second example here. We have vector P, which has magnitude 20 centimeter, and the angle here is 37. So we are asked to find the value of Py and Px here. So be careful, because now the angle is between P and Py. Therefore, I would do the Py first here, and notice that the direction of Py is pointing to downward direction, so the value here is minus, and then the magnitude is 20 times cosine 37, and cosine 37 is around 0.8. Therefore you'll get it's around minus 16 centimeter. Again, this minus is because the Py is pointing downward. And now for the second component, Px here, you can see that this is also equal to Px, and the position is the opposite of 36 degree here. So the magnitude of Px is 20 times sine 37, and sine 37 is equal to 0.6. So here we get around 12 centimeter.